Okay, so I have a presentation which covers pressure hull requirements for passenger submersibles. Okay, next slide. So this presentation basically looks at classification and class societies. We look at the ABS experience with underwater units. We'll briefly look at the submersible rules, regulations, and standards. And we'll also address a few questions on carbon fiber pressure hulls. Next slide. Next. Okay, so what are class societies? So class societies are organizations that publish rules for the classification of ships, offshore facilities, and other marine vehicles such as submersibles. Then they conduct design review and surveys to check for compliance with the rules. And class societies also issue class certificates and maintain a register or a database of ships, offshore facilities, and other marine vehicles that the society has classed. So at present, there are more than 50 organizations around the world that offer classification services. Now, out of these 50, 12 class societies, including the American Bureau of Shipping, are members of the International Association of Class Societies, or IACS. So IACS's mission is to develop minimum technical requirements for the design, construction, maintenance, and survey of ships and marine-related facilities. And IACS also works to assist international regulatory bodies such as the International Maritime Organization and standards organizations to develop and interpret statutory regulations and industry standards. So IACS member societies are typically well-established class societies that are recognized by flag administrations around the world. At present, IACS member societies are responsible for classing around 90% of the world's maritime tonnage. Next slide. So in most countries, by law, only classification societies can class submersibles, ships, and offshore facilities. And the role of classification has been recognized by the International Maritime Organization, or IMO, in the Safety of Life at Sea Convention, as well as other international conventions. So class societies act as recognized organizations, performing statutory inspections, as well as design review on behalf of flag administrations. Next slide. So the classification process consists of a number of steps which are described in Part 1A of the ABS Rules for Conditions of Classification. So what are these steps? The first step is the classification process involves the development of rules, guides, and other standards for ships, offshore facilities, and marine vehicles such as submersibles. Then the next step involves design review and surveys to check for compliance with the rules. The next step is classification of ships, offshore facilities, and submersibles once compliance with the rules has been checked. And the next step is issuance of a class certificate that is valid for 5 years and is endorsed annually after conducting post-construction surveys. So how are the class society rules developed? So these rules are developed by class society engineers and surveyors with the assistance of industry experts. Now these rules are then reviewed and approved by committees that include industry experts, representatives of government organizations, shipbuilders, ship owners, operators, etc. So this process ensures that the rules of the class societies are thorough, they are impartial, and they are practical to apply. Next slide. So classification in essence means that the vessels, offshore facilities, and submersibles are in compliance with the applicable rules. So while classification is a process, the owner or the operator also has a responsibility. So what are these responsibilities? They need to operate the submersible within its design or operational limits. Okay, so all submersibles are designed for specific parameters. If you exceed these parameters, then you're likely to have an accident. So it's very important to operate the submersible within its design and operational limits. Then they are responsible for periodically inspecting and maintaining the submersible. Then they are responsible for crewing the submersible with trained and competent personnel. And they're also responsible for following all applicable statutory regulations of the flag or coastal state administration. So all these are responsibilities of the owner and operator. So the rules provide the minimum criteria for classification. However, owners and operators still need to use an independent judgment when they operate the submersible, and safe operation as well as maintenance of the submersible is the sole responsibility of the owner and operator. Next slide. So what is the classification process for submersible? So this involves a number of steps. The first step is rule development. That means we will develop, establish, and maintain recognized technical standards known as the rules. So the rules provide the baseline for classification. Then once the rules are developed, the class society will conduct design review to check that the design of the submersible is in compliance with the rules. Then the class society will conduct material and equipment certification. So this will verify that the submersible meets the rule requirements and all the materials and the equipment is certified and it meets the rule requirements. So next we have new construction survey. So this will check that the submersible is built as per the rules. And then we have surveys after construction. This will check that the submersible is maintained in compliance with the rules throughout its life cycle. So this is done through annual surveys which are conducted at 1-year intervals and special periodical surveys at 3-year intervals. Okay? So this is a little different from surface vessels. Surface vessels have their special periodical surveys at 5-year intervals. So the question comes, why do we have a 3-year interval for underwater vehicles? This is because this comes from the IMO submersible guidelines, which requires dry docking surveys at 36-month intervals. Okay? So this is the basic process for classification of submersibles. So next we come to the ABS experience with underwater units. Next slide. So since the 1960s, ABS has classed around 100 submersibles worldwide. Now these include some of the first commercial submersibles that were developed in the 1960s and 70s, such as the Perry and Pisces submersibles. Now ABS has also classed some of the latest commercial submersible designs that are available in the market, including submersibles built by companies such as Triton Submarines and Seaimagine Hydrospace. Now currently ABS has around 30 submersibles in class. Apart from submersibles, ABS also has 43 diving systems in class. So these include saturation, mixed gas, and air diving systems. Then we have one submarine rescue handling system in class for the US Navy. Then we have an undersea habitat in class. So this is the Aquarius habitat, which is located underwater off the Florida Keys. And then we have 3 hyperbaric facilities in class. So these are all underwater units that are currently in class with ABS. Next slide. So when it comes to the OceanGate Titan submersible, ABS had no involvement with this submersible. No request for class was submitted to ABS, and no design review or surveys were conducted by ABS. Okay. Next slide. So the Coast Guard asked us about the Antipodes submersible. Now this was a submersible that was owned by OceanGate for a period of time, and it was then sold. So this slide gives a brief history of the Antipodes submersible. So this submersible was built by Perry Submarine Builders out of Florida, and then major modifications were conducted by Marlin Submarines. This is a UK-based company. So they conducted major modifications to the submersible. They removed the lockout compartment. And the slide basically gives a brief history of this submersible. Now the important point is this submersible has a traditional steel pressure hull, and it was designed for a depth of 305 meters seawater or 1,000 feet seawater. Now the submersible maintained its classification during the time it was owned by OceanGate, and it is still classed with ABS. So that's a brief summary of the Antipodes submersible. Next slide. So next slide. Yeah, okay. No, previous slide, please. Okay. Now, the modern day submersible industry started in 1948 with the design and development of the Bathyscaphe FNRS-2, which was followed by the development of the Bathyscaphe Trieste. Now, these Bathyscaphes were designed and developed by the Swiss physicist and balloonist Auguste Piccard. Now, subsequently in the 1960s, the submersible industry started taking off as more and more submersibles were designed and manufactured. So these included submersibles for tourism, recreational, and scientific research purposes. So at that time, the only available requirements for certification of submersibles were the US Navy requirements, and there were no published industry standards for the certification of commercial submersibles. So ABS was approached by members of the industry as well as the US Navy and Coast Guard to develop requirements for the classification of commercial submersibles. So in response, ABS established a special committee on submersible vehicles that included industry stalwarts such as Jack Pickard, John Pritzlaff, Lieutenant Don Walsh, and ABS developed the 1968 guide for the classification of manned submersibles. Now, this was a pioneering document. It was the first set of requirements for manned submersibles that was published by any class society. Now, following the release of the 1968 guide, this guide was updated and then published as the ABS rules for underwater systems in 1979. It was again updated and published as the ABS rules for building and classing underwater vehicles, systems, and hyperbaric 1990. And this edition of the rules incorporated additional requirements of passenger submersibles. So the latest edition of the rules is the 2024 underwater rules. And these rules are updated every year. And all these rules are posted on the ABS website, www.eagle.org. Next slide, please. So now we come to the materials. So when it comes to submersible design, there are two sets of materials that are very tightly controlled. These are materials for the pressure hull and materials for life support systems. Okay? So the pressure hull is a critical component, and it serves to protect the human occupants for the extremely high hydrostatic pressures that are present at depth. So the pressure hull has absolutely no redundancy or backup. So if the pressure hull fails, you've effectively lost the submersible. Okay? So it is very important that the pressure hull be fabricated from robust materials that have a documented service history for external pressure applications. So the ABS rules require pressure hull materials to be fabricated from approved material specifications, and the rules have a list of approved materials for pressure hulls. So these materials are listed on the screen, and they include steels, aluminum, titanium, and acrylic plastics for the windows. Now, all of these materials have many years of documented service history and are considered to be well-established and robust materials. Now, it's important to note here that carbon fiber composites are not approved materials for the pressure hull of submersibles as per the ABS rules. Next slide. So now we have a couple of questions on carbon fiber pressure hulls. So the first question that arises is, why do we need a carbon fiber composite pressure hull? What are we trying to achieve? Okay? So carbon fiber composites are high-strength, lightweight materials. Okay? Now, a pressure hull fabricated from carbon fiber composites would be much lighter from a hull made from traditional materials such as steel or titanium. Okay? So with a lighter hull, what happens is you can reduce the amount of syntactic foam that needs to be carried on the submersible to maintain buoyancy. Then you don't need a crane or a launch and recovery system for launching and recovering the submersible while you're at sea. And since the hull is lightweight, you can increase the size of the hull and accommodate more passengers. Okay? So typically what we have seen is anytime you go below a depth of 1,000 meters seawater or 3,280 feet seawater, the shape of the pressure hull is spherical. Okay? We have not seen cylindrical pressure hulls being used beyond a depth of 1,000 meters seawater. The reason is a spherical pressure hull is the best shape for resisting external pressure. Okay? The stresses are evenly distributed around the hull. So if you take a spherical pressure hull versus a cylindrical pressure hull of the same thickness, when exposed to the same pressure, you will see that the hoop stress in a spherical pressure hull is half that of a cylindrical pressure hull. Okay? So if you see a cylindrical pressure hull being used beyond 1,000 meters, it is pretty unusual. Okay? So now, what are some of the key concerns with the carbon fiber composite pressure hulls? So the first thing is carbon fiber composite pressure hulls are anisotropic. That is, the mechanical properties vary with direction. Okay? So the mechanical properties are strongest in the direction of the fibers. When the fibers are loaded in tension, that is when the carbon fiber composite is the strongest. But if you go in other directions, the composite is not so strong. So when the composite is exposed to external pressure, the pressure will act perpendicular to the direction of the fibers. And that is not the strongest direction of the carbon fiber composite. Okay? So this is very different from traditional materials such as steel or titanium, which are isotropic. That is, the mechanical properties are same in all directions. Okay? So the next thing is carbon fiber composites are a combination of carbon fiber strands in an epoxy matrix. The carbon fiber is strong in tension, weak in compression. The epoxy, on the other hand, is strong in compression and weak in tension. So the composite is a combination of these two materials. The characteristics of these two materials are combined together to create the composite. Okay. So the next thing is carbon fiber composites do not exhibit plasticity or ductility similar to steels. Okay. So carbon fiber composites, if you look at a stress strain curve of carbon fiber composites, the relationship between stress and strain is nearly linear up to the point of failure. Okay. So this curve does not have a well-established yield point because there is no yielding of the material. So the material goes all the way to its failure point and then it catastrophically fails with little or no warning. So this is very different from traditional materials such as steel or titanium. Because in steel or titanium, once you reach the yield point, the material starts deforming. And then you reach the ultimate tensile strength and it deforms further and then the material fractures. So there is plastic deformation of the material from the yield point till the time it fractures. Okay? And then strain hardening of the material takes place till you reach ultimate tensile strength. And after that, there's something called necking or the reduction in area of the material. Okay? So this effect is not seen in carbon fiber composites. Okay? So they go directly to the point of failure and then suddenly fail. So then the next thing is prolonged exposure to UV radiation can cause the epoxy to get damaged. Okay? So what happens is the epoxy, in some cases, you add something called a UV stabilizer. It's a chemical that's added in the epoxy, and that protects the epoxy from UV radiation. In some other cases, you can have a gel coat or a top coat which is placed on the epoxy. For example, you can have a polyurethane coating, and that protects the epoxy from the damage caused by UV radiation or the sunlight. Okay? So if you don't have this protection and you expose the carbon fiber composite to sunlight, the UV radiation will degrade the mechanical properties of the composite. Okay? So next thing is under extreme high pressure applications, carbon fiber composites are susceptible to fatigue damage under repeated external pressurization and depressurization. And the accumulated damage may remain hidden and may not show up. Okay? So the important thing here is unless the fatigue failure shows up as cracks or delamination, you really cannot see the damage. It may remain hidden in the carbon fiber strands. Okay? So once you have a crack or a delamination, the extreme high water pressures will accelerate the growth of the crack or the delamination. And the crack will grow very fast. Okay? And then you can have collapse or failure of the pressure hull. So the next thing is carbon fiber composites are not sensitive. They are sensitive to local damage. So if you have a cut on the surface from a mechanical impact, this can grow to form a crack, which can lead to failure of the pressure hull. Okay, so it's very important to protect carbon fiber composite pressure hulls from impact loads. Okay, and then saltwater ingress in the epoxy matrix under extreme pressures can lead to delamination. Okay, now epoxy resins in general are highly resistant to saltwater damage. However, if you have voids in the epoxy, okay, we have air pockets. Salt water can accumulate in these air pockets, and over time, this can form saltwater crystals. And then over several pressure cycles, this can cause delamination of the pressure hull under extreme pressures. Delamination means separation of the carbon fiber plies. Okay? So that is another damaging effect that is possible in carbon fiber composites. Next slide, please. So one of the processes used for fabricating carbon fiber composite pressure hulls is the filament winding process, in which the pressure hull is created by impregnating or coating the carbon fiber strands with epoxy and then winding them in a precise geometric fashion over a mandrel. So a mandrel is basically a tool in the shape of a cylinder. So on the cylinder, you wind the carbon fibers which are impregnated with epoxy. And then you cure that cylinder in an oven at 1 atmosphere or in an autoclave under pressure. Okay? So in a thick carbon fiber pressure hull, there may be several layers of carbon fiber composites, and these layers cure at different rates. So what you will have is several layers with different mechanical properties since they were cured at different rates at different times. Okay? So manufacturing a thick section of carbon fiber composites with consistent mechanical properties throughout the thickness is difficult. Okay? So the mechanical properties of the finished product or the finished carbon fiber pressure hull depend on a number of factors. So these include the number of layers and the thickness of the carbon fiber composites. So the more the number of layers and the greater the thickness, the more difficult it is to achieve a pressure hull with consistent mechanical properties throughout the thickness. Another important consideration is the winding orientation. Now, a typical thick shell pressure hull is exposed to hoop stresses, radial stresses, as well as longitudinal stresses. Okay. Now, if your winding is hoop winding, that means if you wind the carbon fiber composites around the cylinder in a hoop fashion, that is only good for withstanding hoop stresses. It cannot withstand radial or longitudinal stresses. So to withstand radial or longitudinal stresses, you typically employ X cross winding. That means you wind it in an X pattern, okay? And that is more effective in handling hoop as well as radial as well as longitudinal stresses. Then the type of epoxy resin that is used for creating the composite has an impact on the strength of the pressure hull. So aerospace grade epoxies may not be suitable for high pressure underwater applications, okay? So then there are other factors such as the epoxy wetting rate. That means how much epoxy can you coat on the carbon fiber strands. Then the epoxy curing rate. If you don't follow the correct curing profile, your mechanical strength may differ. Then humidity is another important consideration. So high humidity during curing of the composite can negatively impact the mechanical properties. This is because moisture absorption in the resin can lead to delamination and reduced interfacial strength between the carbon fiber and resin, thus weakening the composite. Then curing the carbon fiber composite at the proper temperature is very critical. So if you don't follow the exact temperature profile when you cure the carbon fiber composite, then it will affect the mechanical properties. If you don't properly cure it, the mechanical properties can be degraded. So pressure is another important consideration when you cure your carbon fiber composite. So the composite can be cured at 1 atmosphere in a standard oven, or it can be cured under pressure in an autoclave. So autoclave is basically a pressurized oven. So the pressure will basically drive out the air pockets in the carbon fiber composite and will compress the carbon fiber composite. So you get a better product if you cure your carbon fiber composites in an autoclave versus curing it in an 1 atmosphere oven. Okay, so then the other aspect is manufacturing defects such as voids, porosity, blisters, inclusions can have an effect on the strength of the carbon fiber composite. So voids are basically air pockets within the thickness of the carbon fiber composites. Blisters are formed on the surface of carbon fiber composites. Then you can have porosity. Porosity means a large number of voids in a close proximity to each other. So all of these can weaken the carbon fiber composite sections, and under extreme hydrostatic pressure, they can accelerate the collapse of the pressure hull. So the next thing that's challenging is bonding of carbon fiber composites with metallic elements. So typically, if you bond a carbon fiber composite with a metal, what you will do is you'll have projections coming out of the metal. Typically, you will have fins, and these projections go in the carbon fiber composite, and they help in getting better adhesion. So in addition to applying an adhesive, you have to have co-lamination. That ensures you have better adhesion between the carbon fiber composite and the metallic element. Now, galvanic corrosion is an important consideration here because if the metal comes in contact with the carbon fiber strands in the presence of seawater, you can have galvanic corrosion. So this typically occurs in steels and aluminum, and that can cause corrosion of the metallic members. Okay. Next slide, please. So now carbon fiber composites have a low modulus of elasticity, they have low shear strength, and they are brittle materials with low impact strength, okay? So they have very low resistance to impact loads, and the hull is susceptible to deformation under applied external loading. So typically lifting lugs and other attachments are not directly installed on carbon fiber composite pressure hulls because they cannot withstand localized loading, and they tend to deform under localized loading. So then if you install penetrations on the carbon fiber composite pressure hull, that means you have to make openings in the pressure hull. That will weaken the pressure hull because the main load-bearing member in a composite are the carbon fiber strands. So if you cut the strands to make an opening, you're going to weaken the pressure hull. So reinforcement of the openings is very critical. And if you don't reinforce it, you can have stress razors in the vicinity of the opening, and that can lead to cracks and failure of the pressure hull. Okay. So then when you design your carbon fiber pressure hull, you also need to consider various failure modes, including delamination, debonding, fiber breakage, and matrix cracking. Okay. So delamination basically means separation of the carbon fiber plies. The plies start separating. Then debonding basically means when the carbon fiber strands start coming out from the epoxy matrix. Okay. So debonding is caused by failure of adhesion between the strands and the epoxy matrix. Okay. And then matrix cracking is basically characterized by cracks in the epoxy matrix, and this occurs due to fatigue of the material. Fiber breakage occurs when the carbon fiber strands will snap or break. Okay, so this can be caused by high stresses, they can be caused by impact loads, or due to manufacturing defects in the carbon fiber. Now, since the carbon fiber strands are the main load-bearing member in the composite, if you have strands that break off, then the strength of the hull will deteriorate, and you can have premature collapse of the pressure hull. Okay. So then, when it comes to metallic pressure hulls, there are well-established failure modes and factors of safety that have been proven over many years of service experience. Okay, so the figures on the screen show some of the typical failure modes for metallic pressure hulls. The first figure shows local yielding. So local yielding occurs when the section of the pressure hull between two adjacent stiffeners fails. Okay, you have yielding between two stiffeners, and then the hull will take the shape of an accordion pleat. So that is called local yielding, and the factor of safety for local yielding in the ABS underwater rules is 1.5. Then you can have local buckling. Local buckling occurs when the section of the pressure hull between two stiffeners buckles. Okay, so you'll have dimples formed in the pressure hull, and that is known as local buckling or low bar buckling. And the factor of safety for this buckling in the ABS underwater rules is 1.25. And the third failure mode, which is the figure on the far right, is general instability or overall collapse of the shell and stiffener section. Okay, and the factor of safety in the underwater rules for this failure mode is 2.0. So all of these failure modes are well established. They have many years of service experience, and the factors of safety are well proven through service experience on many different submersibles. Now, additionally, the rules also have a well-established acceptance criteria for hull out of roundness and local departure from design geometry. So when you have a pressure hull which is exposed to external pressure, it is very important to maintain out of roundness of the hull. Okay, so if the out of roundness of the hull goes beyond specifications, it can cause premature collapse of the hull. So out of roundness is absolutely critical when you have a pressure hull which is exposed to external pressure. Next slide, please. Okay, so currently there are no recognized national or international standards for carbon fiber pressure hulls for human occupancy. Okay, so we have the ASME Boil and Pressure Vessel Code has section 10, which addresses fiber reinforced plastic pressure vessels. But if you look at the scope of section 10, it states that pressure vessels for human occupancy are not covered under this code. And then we had a look through this code. It addresses pressure vessels that are used for surface applications. It really does not address pressure vessels that are used for deep sea diving applications. We had a look at the testing requirements. So many of the testing requirements are geared towards internally pressurized pressure vessels. We didn't see any specific testing requirements for externally pressurized pressure vessels. Okay, so these are some of the shortcomings of section 10. And this section is not applicable to manned pressure hulls. Okay, nevertheless, it has a lot of useful information. It has acceptance criteria for voids, delamination, cracking, etc. The important thing is this code states that for a new construction pressure hull, no delamination and no cracking in the matrix is permissible. Okay, so if you have a new hull with delamination or cracks, it is not acceptable as per this code. Okay, so when it comes to carbon fiber composite pressure hulls, you know, the different failure modes, the factors of safety, as well as the other acceptance criteria is not really defined in international standards, as well as class society rules. Okay, so one of the very important failure modes for thick shell carbon fiber composite sections under external pressure is snap through buckling. Okay, now snap through buckling is an effect that has been observed in subsea pipelines made of glass fiber reinforced plastics. Okay, Now, this buckling causes sudden and catastrophic failure of the pressure hull, okay? And it is thought to be triggered by shape imperfections. For example, if there is out of roundness, that can trigger this buckling, okay? Now, snap-through buckling is different from traditional buckling, which is caused by progressive overpressurization of the pressure hull beyond its design depth. So when snap-through buckling occurs, it causes instantaneous delamination of the pressure hull and instantaneous collapse of the pressure hull, which can occur in less than a millisecond, okay? So if you have sensors for real-time monitoring, it will not pick up any signs of this failure before it occurs, okay? Now, snap-through buckling is a phenomenon that is not yet well understood, okay? So additional theoretical and experimental research is needed to determine what are the factors that cause this failure mode, what factors of safety are needed to avoid this failure mode, and what do we need to do to guard against this failure mode. So this is something that is not addressed in international standards. It is not well understood. Nevertheless, this effect has been observed, and we need to have further research and testing in this area. Okay, so the other thing is when you do your design calculations for carbon fiber composites, these materials are anisotropic. That means the mechanical properties vary with direction. The mechanical properties through the thickness may vary, okay? And they're also dependent on the manufacturing process. So all of these can vary the mechanical properties of the finished product. So when you do your design calculation, it's very important that you test coupons from the as-built product. So how this is done is you will typically extend the length of the cylinder, okay? This is called prolongations. And from there you will cut coupons. Coupons are basically sample of materials that you then send to a lab for testing. So after it's sent to the lab for testing, you will evaluate various mechanical properties. These include the tensile properties, what's the ultimate tensile strength, what's the tensile modulus, the compressive strength, the flexural strength, the shear strength. All of these properties are evaluated, and then you'll get the test results. And those test results are what is used for your design analysis, okay? So if you don't use those test results, what you design may not match what you have produced, okay? This is a little different from traditional, pressure hull materials, because when we do the design review of traditional pressure hull materials, the material allowables and the mechanical properties come from the material specifications, okay? You typically do not use the as-tested mechanical properties because they may exceed the material allowables. If they don't exceed, the material is rejected, okay? But the as-tested properties are typically not used when you design pressure hulls made of steel or titanium, because the properties you use there come from the material specification. Those define the minimum acceptable properties. Okay, next slide, please. So next we come to non-destructive inspection of thick carbon fiber sections. So if you have a very thick carbon fiber section, for example, a 5-inch thick section, ultrasonic examination may not be suitable because of lack of penetration of the ultrasonic waves and lack of reflection, okay? So using UT, you may not be able to evaluate a thick carbon fiber composite sections. So for thick carbon fiber composite sections, you will use non-destructive techniques such as X-ray computed tomography, or you can use active thermography, okay? So X-ray computed tomography, basically you have an X-ray machine that goes around the circumference of the pressure hull, and you have various slices. You have images in slices. All these images are combined together using software, and you get a 3D image of the hull, okay? Then you have an in-depth look, what is going on inside the hull. So this inspection basically requires you to strip down the pressure hull. So if you have a pressure hull that is in service, and now you need to do a non-destructive examination, you need to remove all the equipment, all the outfittings on the pressure hull, okay? Now, if you do not have this equipment at the facility where you're maintaining the submersible, then you need to ship the submersible hull to another facility where they have this specialized equipment. Now, after doing the ND, if repairs are required, you may need to repair the pressure hull, okay, and then ship it back. So all this is an expensive and a long process, and it may not work practically for a submersible that is in operation, because you need to take it out of operation for many months at a time, okay? So these are some of the challenges that you will face if you use a carbon fiber composite pressure hull, okay? Next slide, please. So for carbon fiber composite pressure hulls, it is very important to verify that no deformation is taking place, no degradation is taking place, or no flaw development is taking place that may weaken the pressure hull. So these needs to be done periodically over the service life of the pressure hull. Now, the post-construction inspection and testing criteria for carbon fiber pressure hulls are currently not addressed in recognized international or national standards. As a minimum, they should address non-destructive examination criteria. Okay, so what kind of non-destructive examination is required? What is the periodicity, and what is the acceptance and rejection criteria for this examination? Then, what are the dimensional measurement criteria for out of roundness and local departure from design geometry? Okay, so how much out of roundness is permissible? This is currently for a carbon fiber composite pressure hull. This is currently not addressed in international standards. And then, what are the test dive requirements periodically for carbon fiber pressure hulls? Okay, so all of these are not addressed currently, and they need to be addressed. Next slide, please. So then the question comes up, do existing class society rules, statutory regulations, or industry standards address carbon fiber pressure hulls for submersibles? So under the ABS underwater rules, carbon fiber pressure hulls are not acceptable materials for submersibles. Now, to the best of our knowledge, the requirements of other IX member class societies, as well as existing industry standards or statutory regulations, do not have specific requirements for carbon fiber composite pressure hulls. Okay. Now, we are aware that a number of ASME PVHO cases have been developed for the use of non-metallic materials for pressure vessels or human occupancy. Okay, so what is an ASME PVHO case? Now, if a designer or builder wants to deviate from the published requirements of the ASME safety standard, then they develop something known as an ASME case. Okay, so this ASME case is then submitted to the ASME PVHO standards committee, and the standards committee will review the case and then they will approve it. Okay, once the case is approved, it is they place it on the ASME website. Okay, so all the published cases are put up on the ASME website, and anyone can use a published case. So ASME has a mechanism by which, if you want to deviate from the published requirements, you develop a case, and that is published, and it is put on their website. So this is similar to the code cases that are developed for the ASME boil and pressure vessel code. Okay, so a lot of code cases have been developed. Now, some of the ASME PVHO cases that have been developed are for surface-based internal pressure applications. For example, medical hyperbaric chamber, transfer trunks for diving, etc. All of these operate at relatively mild pressures. So these operate in the range of 4 to 80 psig. Okay. So in comparison, if you go down to a depth of 4,000 meters seawater, the pressure there is 5,800 psi. Okay. So there's a huge difference between the pressures for these ASME PVHO cases versus the external pressure at a depth of 4,000 meters seawater. Now, case number 11 addresses a non-metallic expansion joint that was used as a transfer trunk or tunnel between two pressure vessels of human occupancy. This was designed for the Navy submarine rescue system. Okay, this is basically an expansion joint that connects two PVHOs. And the materials used were neoprene, polyester, and a fluoroelastomeric compound. Then case number 12 was a non-metallic portable hyperbaric stretcher, and the material used was a liquid crystal polymer tube, which was enclosed in polyurethane and which was then coated with nylon. And the maximum pressure for this application was in the range of 33 to 75 psig. So all of these are for internal pressure applications, and they are for very mild pressures as compared to the pressure at a depth of 4,000 meters seawater. Okay, next. So then the question comes up, do class society rules allow you to use alternative requirements or equivalent standards for carbon fiber PVHOs? So while the ABS rules do have provisions for alternative arrangements and novel concepts, in the many decades that we have been classing submersibles, these alternatives have not been used for carbon fiber pressure hulls. Now, if you have non-standard designs, materials, there is a mechanism in the ASME PVHO standard by which you can get approval. Okay, so if you look at the ASME PVHO standard, non-mandatory Appendix D has guidelines for developing a PVHO case for the use of non-standard materials or non-standard designs. Next slide. So this slide basically gives a brief overview of non-mandatory Appendix D in the ASME PVHO 1 standard. And these are basically guidelines for qualifying non-standard designs and non-standard materials. So as the first step, detailed design information on the proposed materials along with the detailed design analysis, which consider all applicable loads and environmental conditions need to be developed. Thereafter, you have to conduct prototype testing. So this testing involves, uh, there is proof pressure testing. So for this proof pressure testing, 3 full-scale pressure hulls are tested to 6 times maximum allowable working pressure or MAWP without failure. So this is basically a factor of safety tests, okay? So you'll test the hull to 6 times its design pressure, and if it does not fail, that qualifies the design. The next testing is creep testing. So under creep testing, so what is creep? Creep basically means under sustained hydrostatic loading, does the pressure hull deform? Okay, that is creep. So for creep testing, you will use model or full-scale pressure hulls, and they are subject to 10,000 hours of sustained pressurization without failure. So 10,000 hours basically means 1 year and 1.5 months. So for you will pressurize the hull and maintain the pressure for 1 year and 1.5 months, and then you check if the hull has deformed or it has failed by creep. Okay, so the options available include you test 1 pressure hull to 3 times MAWP, or you test 5 pressure hulls to 2 times MAWP. So after the creep testing, the next thing is a cyclical pressure testing. This is basically a fatigue test. So then you take a full-scale pressure hull, and then you will cyclically pressure test the hull for a number of pressure cycles. So the approved operational pressure cycles will basically be half the number of cycles you tested minus 1,000 cycles. Okay, so that is how you get the fatigue life of the hull. So once you conduct the prototype testing, you have qualified the prototype. So the next thing is you build the production unit, and thereafter you'll do a hydrostatic pressure test to 1.5 the design pressure, and then you'll maintain the pressure for 1 hour. Now for this case, all the testing needs to be witnessed and signed off by a third-party independent agency such as a class society. Okay, so these guidelines provide very, very clear requirements for non-standard designs and materials. You can follow these guidelines anytime you have non-standard designs or materials. So there is a mechanism in the industry for qualifying non-standard designs and materials. Next slide, please. So then when it comes to hydrostatic pressure testing requirements for pressure hulls, what are the ABS rule requirements? Now these rule requirements are for metallic pressure hulls, okay? So the ABS rules require your pressure hull to be hydrostatically pressure tested to 1.25 times the design depth for 2 cycles, okay? And when you do this pressure testing, you have to strain gauge the pressure hull. Strain gauges are to be fitted in way of hard spots and discontinuities. Hard spots is a spot where the hardness is slightly different from the other sections of the hull. Discontinuity could be a sudden change in the geometry or the loading or the material of the hull, okay? So all of these spots would be strain gauged. And then the strain gauge measurements are recorded after shakedown effects have ceased, okay? So the question comes, what is shakedown, okay? So in a new construction pressure hulls, you will notice their localized area of high stresses on the hull. So when you pressure cycle the hull above its design pressure, what happens is these localized area of high stresses start deforming, okay? So you'll have localized deformation and then strain hardening occurs. Once the strain hardening occurs, no further deformation of the hull occurs plastically. All the deformation is in the elastic region, okay? So that is when the shakedown effects cease. So what happens if you pressure test the hull and start recording the strain gauge measurements before shakedown has ceased? You will note that the strain gauge measurements on the first and second cycles do not match. That is because shakedown is still taking place. So after shakedown has ceased, you will see the pressure, the readings on the strain gauge on the first and second cycle, they will match, okay? So typically to verify that shakedown has ceased, you will pressure cycle the hull for a number of cycles, and then you will check the strain gauge readings. Once you confirm that the readings match, that is the point when shakedown has ceased, okay? And those are the readings you actually use for your hydrostatic pressure testing. So then once the hydrostatic pressure testing is completed, the designer will submit a report comparing the calculated stresses versus the measured stresses. There should be a good correlation. If there's not a good correlation, we'll ask the designer to justify what's happening why is the calculated versus the measured stresses varying, okay? And then once the hydrostatic pressure test is completed, you'll have non-destructive examination of the hull. So this is done by surface ND techniques such as magnetic particle testing, dye penetrant testing, or eddy current testing, okay? And then out of roundness measurements are taken, and then we verify compliance with the acceptance criteria in the ABS underwater rules, okay? Now these out of roundness measurements after hydrostatic pressure testing are used as reference measurements throughout the life of the submersible, okay? So 5 years down the road, if you want to check what were my original readings, what my readings now, these are the reference readings that you will use throughout the life of the submersible. So it is very important to have a reference set of readings which you will use for the life of the submersible. Next slide, please. So then we come to the ABS rule requirements for test dive of new construction submersibles. So after the pressure hull is built and it is fully outfitted, we conduct a test dive. Okay, so before passengers get on the submersible, you have to do a test dive in the presence of the ABS surveyor. So how do you do this test dive? Okay, you start diving and you increase your depth at 20% increments. So you first dive to 20% of your design depth, you stop, and then you will start internally inspecting all your wells, all your hatches, you will inspect your windows, and you will check your pressure boundary valves, make sure there are no leakages, okay? If everything is good, then you continue test dive for another 20%, okay? In this manner, you keep going down till you reach your test depth, okay? And once you reach your test depth, you functionally test all your systems, your life support systems, your electrical systems, and other essential systems, okay? So this is a test dive. This qualifies the submersible for diving at that particular depth. Sometimes what happens is when you go for doing a test dive, the depth of the water may not be equal to your design depth. Your design depth may be deeper than the dive at which you tested the submersible, okay? So the depth at which you tested the submersible is known as a rated depth, okay? So when we class a submersible, we will class it for the rated depth, okay? And later on, if you want to increase the rated depth, you can do another test dive, okay, beyond the rated depth, but not exceeding your design depth, okay? So there are two depths that are very important, design depth and rated depth, okay? Next slide, please. So then we come to post-construction surveys. So during the annual surveys, this is basically a visual examination of the pressure hull. So the surveyor will go and inspect the pressure hull. They will inspect the hatches, the sealing surfaces, penetrations, the welded joints, viewports, foundations, and the shut-off valves on the pressure hull. So this is a visual examination to make sure that there is no degradation, there's no leakage, etc. And this is done every 1 year. Then the special periodical surveys are conducted at 3-year intervals. Now, during this survey, we have enhanced examination of the pressure hull. So this requires removal of your protective coatings as well as thermal insulation in selected locations. And then if you have highly stressed parts such as the lifting lug wells, they are non-destructively examined using surface ND techniques such as dye penetrant testing, eddy current testing, etc. And then if the surveyor suspects there is deformation of the hull or there is damage to the hull, then the surveyor may require out of roundness measurements to be taken for the hull. And these would be compared with the reference measurements as well as the acceptance criteria specified in the rules. So if you exceed the acceptance criteria in the rules, then the pressure hull is rejected. Okay, you have to repair the pressure hull, bring it back in spec. Otherwise, you cannot dive. So then we also require a test or operational dive. So during the annual surveys, we require an operational dive to be conducted every year. And during our special periodic surveys, we require a full depth test dive to be conducted in the presence of the surveyor. And this dive is to demonstrate proper functioning of the systems and equipment at the full depth. Okay, next slide. So then we come to the IMO submersible guidelines. So these guidelines were developed by the International Maritime Organization, or IMO, back in 2001. Okay, so the intent of these guidelines was to provide an international standard that could be used by flag administrations around the world. Okay, now compliance with these guidelines is voluntary, since the IMO Solas Convention does not mandate that you have to comply with these guidelines. So compliance is voluntary. Unless the flag administrations require you to comply with these guidelines, designers or operators may not comply with these guidelines, okay? And then these guidelines require the pressure hull, materials, fabrication, and testing to comply with the requirements of a recognized organization to the satisfaction of the administration. Okay, so a recognized organization is typically a class society. Okay, so if you want to comply with the IMO submersible guidelines, it means that your pressure hull needs to meet the requirements of a class society. So then it also requires the issuance of a design and construction document by the administration. So this document will list the standards, the design and construction standards for the submersible. And then it also requires the administration to issue a safety compliance certificate after the initial surveys of the submersible are conducted. So typically the design review and surveys would be conducted by a recognized organization, such as a class society, on behalf of the flag administration. And then this submersible guidelines also require the management of the passenger submersible operations to comply with the International Safety Management Code, or ISM code. Okay, so that's a brief overview of the IMO submersible guidelines. Next slide, please. So then we come to the US Coast Guard Navigation and Inspection NVIC, Navigation and Vehicle Inspection Circular 593. This provides guidance for the certification of passenger submersibles. So these guidelines were developed back in 1987 when the Atlantis passenger submersibles were being classed. The Coast Guard worked closely with Atlantis, and these guidelines were developed. They were tailored to the Atlantis submersibles. Okay, so currently, if you're under 100 gross tons, okay, subchapter T of 46 CFR has requirements for passenger vessels under 100 gross tons, but these apply to surface vessels. Okay, these typically do not apply to submersibles. So to develop equivalency to these requirements, this NAVIC was developed, and this was published back in 1993. So now this NAVIC applies to submersibles carrying one or more passengers for hire. This is as per the 1993 Passenger Vessel Safety Act. Okay, and this requires the pressure hull to meet the ASME PVHO standard or the ABS underwater rules. Now this NAVIC applies to US flag submersibles or submersibles operating in the US jurisdiction. So it does not apply to non-US flag submersibles or submersibles operating in international waters. Okay, so that's a brief overview of this NAVIC, and that's all I have in the slides.
Thank you, sir. Appreciate your willingness to answer some questions from the Marine Board in that presentation.
Absolutely.
We'd like to take